Current of electricity. In today's session, we'll be learning about potential difference and power. Under that, we'll be defining potential difference. We'll be recalling and using this term volt is equal to work done over charge. We'll be deriving the equation for power as P is equal to VI, or P is equal to I square R, and P is equal to V square over R. Electromotive force, EMF. Electromotive force is the energy transferred per unit charge when other type of energy is converted into electrical energy. So it is very simple. EMF means the energy that is required by unit charge, but this energy is going to be converted from other form to electrical energy. For example, a battery. If you take a battery, a charge will pass through the battery to the circuit. In that case, the charge will have electrical energy, which will be converted to electrical energy. So the other form of energy that we consider for a battery is chemical energy. So there is a transfer of chemical energy to electrical energy for moving one charge over the circuit. So you can write EMF as energy per unit charge. But what is this energy? It is the energy converted from other form, any forms. In case of battery, it's the chemical energy to electrical energy. Potential difference. Potential difference between any points in a circuit is measured of the electrical energy transferred or work done by unit charge as it moves from one point to the other. So potential energy is somewhat similar to electromotive force, the EMF, but in this case, the energy that is being transferred is between 2 points in a circuit. In other words, potential difference is an electric energy that is transferred per unit charge when electrical energy is converted into another form of energy. So for example, let's consider a battery connected a closed circuit with a bulb. So if the charge passes from the battery to the circuit, then there is a transfer of chemical energy into electrical energy. That is for EMF. Now that the charge is carrying electrical energy, when it passes from the circuit to the bulb in the circuit, now this is going to give us light energy. So as you can see, electric energy of a unit charge has been transferred as light energy. So the energy required by unit charge to transfer from electrical energy to other form of energy, in this case it's the light energy, is known as potential difference. Potential difference and electromotive force both have the same SI unit, which is volt, written as V. And as you can see, EMF or PD, they both is nothing but the same thing, work done per unit charge. Work done by unit charge, work done or energy transfer, that is joule per coulomb. So in other words, I can say the unit volt is equivalent to joule per coulomb. So you can write in a short, PD is the energy over charge, but this energy is converted from electrical to other form. In terms of bulb, the other form is going to be light energy. But if it's a resistor, then when a charge passes through a resistor, it's going to give out the other form of energy as heat energy. Comparing EMF and potential difference. Electromotive force and potential difference both have the same unit, that is volt. They both can be measured using voltmeter. These are the similarities. And as we have seen the definitions, the energy transferred for a unit charge is going to be from other form to electrical in terms of electromotive force. For potential, the energy transfer is going to be from electrical to other forms. So that is the difference. And also, mostly the symbol of EMF is denoted as capital E, but do not confuse with this E and energy. They mean totally the different term. The symbol for potential difference is normally given as V. Let's move on to electric energy and electric power. Now that we have seen that PD or EMF can be summarized as energy per charge, let's take this energy. This energy is also known as electric energy as the subject. If I consider electric energy as the subject, it's going to be VQ, potential difference into charge, or EMF into charge. And we also know that current is the rate of flow of charge. So we can take it as I is equal to Q over T. If I make Q as the subject, I'll get IT. Substitute the value of Q in place of this Q. So I get electrical energy as VIT. The another equation that I can obtain is V is equal to IT. This V is equal to IR. This is an equation that is obtained from Ohm's law. In place of V, we substitute IR. So we get I square RT. Another equation, what we can do is we take VIT from here. Instead of substituting V in place of V, we make I as the subject. From here, I as the subject, which is I is equal to V over R. Substitute V over R in place of this I. Then we get V into V over RT, that's equal to V squared T over R. In short, we can write electrical energy is equal to VQ. This is coming from the definition of EMF or PD. Then it can be also VIT. This is coming from the combination of the current's definition. Current is equal to rate of flow of charge. And from here, we can derive these two equations, I square RT, V square T over R, using Ohm's law equation. Now that we know that power is energy over time, take this energy value, divide by time. Take the energy and divide by time. When we simplify, we get the answer as power is equal to VQ over T, or VI. This equation comes by cancelling T here, or I square R is by cancelling T here, or V square over R cancelling T here. The unit of power is watt. That's the same for all the equations. So using these equations, we can solve any questions that is related to electrical energy and power if any of the term potential difference or charge or current or resistance is known to us. The next video is about resistance and resistivity, so please stay tuned. If you like this video, please subscribe to my channel and press the bell button to get notified with new videos. Thank you.